Hey everyone. So I'm kind of throwing in this random lesson. I never know where to teach it, and I kind of like to leave it for a day where I want an easy lesson along with whatever else we're doing. So we're gonna be talking about linearization of a function. So pause and do the do now. All right. So tangent line. They gave us the point 2, -1, so we just have to find the derivative. So derivative is 2x. Change my color. 2x plus derivative of 3x is 3y squared plus 6xy dy dx plus 3y squared dy dx equals 0. And then everything that does not have a dy dx, so this guy and this guy is going to go to the other side. And I'm going to factor out the dy dx for these. So dy dx times, we're left with 6xy plus 3y squared. And then the 2 underlined are going to go to the other side. Negative 2x minus 3y squared, and then we divide. So negative 2x minus 3y squared all over 6xy plus 3y squared. And then we're going to plug in to find our slope. So let's see what we get. So 2, -1. So let's see, -4 minus 3 on top. And then on the bottom, let's see, that's -12 plus 3. So that's -7 over -9. Did I do that right? Did I make a mistake? No, so 7 over 9 is my slope. So that means this is my m, and then that's my point. So y plus 1 equals 7 over 9, x minus 2. And that is it. So now the reason we're bringing this up, so that's finding our tangent line. And then one of the things they'll say is, does the tangent line lie below or above the curve? So think about how we would figure that out. How do I know if the tangent line's above or below? Well, if the curve looks like this, it's below, right? If the curve looks like this, it's above. If you look back at the definition of concavity, it's actually that the tangent line lies above or below. So what we would do is we'd find the second derivative, plug in. If it's concave up, the tangent line lies below. If it's concave down, like this one, the tangent line would be above. So linearization is when you zoom in to a graph, the closer and closer you get, the graph looks more and more like a line, right? So if we zoom in like right in here, right, and really even closer to that point, you can't even tell the difference between the line and the curve. So it's saying that you can kind of estimate a graph at a point using the tangent line because they're so close together. So a linear approximation, we call it L of x, the linear approximation to a differential function is given by, this is just a fancy tangent line. L of x is our y. This is our y0. This is our m. Whoops, that's a plus. Plus m x minus x0. It's literally just the tangent line where the y0 was brought to the other side, right? Normally it's y minus y0 equals mx minus x0. So all they did was bring the y0 over, and then we're naming it L of x for linearization. So this is it's really nothing new. It's just we're estimating the y value using a tangent line. Okay, so find the linear approximation to f of x near 0. So that means find the linear approximation. That's saying find the tangent line at 0. So we need our point. So 0, what's sine of 0? 0, 0. So now we need our slope, right, m. So f prime, what's the derivative of sine? Cosine. what's f prime of 0? That's just 1, right? So L of x is just 1x, right? So think about it. If we have the graph of sine, right? That's a terrible graph. I'm sorry, guys. Sometimes my brain doesn't work right. Okay, so let's see. So they're saying at 0, the line y equals x is pretty close to the graph. Like, it's right there, right? So if we know the tangent line, we can kind of estimate close to 0. You can't get too far away, because if you get too far away, then it's not going to work. Like, it's not going to be as accurate. But it's an estimate as long as you're close. So we can estimate sine of negative 0.3 using our tangent line. So it's just x, right? So it's just saying that we can estimate that as the y value of sine would just be negative 0.3. L of 0.1 is just 0.1. Oops, sine of 0.4 is 0.4. And then 0.5 is 0.5. Now notice we're getting farther and farther away. Right? So L of pi over 4 is pi over 4. So let's see how close we are. All right. So what I'm going to do is I'm going to grab my calculator and get the actual decimal approximation for each of these. All right. So let's see what we actually get when we plug in. So I wrote them all down. So notice around 0, it's pretty accurate, right? So we go with negative 0.3, and was that supposed to be negative? Did I not plug the negative in? It must be a negative. Like, that's really, really close, right? If we round out to 1,000th, this is pretty close. So this is close, this is close. Getting a little far away, right? We're off by 200ths. I mean, it depends on what close means to you, right? So all of these are pretty good. I think the first two definitely super close. The margin of error is pretty low. 0.4, 0.5, getting a little farther away. And then pi over 4, which is 0.78. We're off by, 700ths or 800ths. So it is pretty accurate, though. Okay, so use a linear approximation of f of x to estimate the value of root 66. So we're going to, remember, a linear approximation is just a tangent line. So find the tangent line, right? But notice they're not giving us a point. What do you think the point should be? So we want something close to the square root of 66. What perfect square do we know that's close? 64. Right? What's the square root of 64? 8. So our point is 64, 8. Now we need our slope. Right? What's the slope of root x? 1 over 2 root x. So f prime of 64 is 1 over 2 times the square root of 64. So that's 1 over 2 times 8, 1 over 16. Right? So our L of x, our linear approximation, is 8, right, our y value, plus 1 over 16, x minus 64. Right, so you start with your y0 and then add m times x minus your x value. So I'm going to plug in what we want to estimate, L of 66. So 8 plus 1 over 16, 66 minus 64. So that's 2 over 16. That's 1/8, 8 and 1/8. So that's my estimate. 8 and 1/8 is 8.125. Let's look at what the actual answer is. Right? The estimate. The square root of 66, let's see, is 8.124. So that's really a good estimate. So this, before calculators, this was a really good way to estimate a square root without a calculator. Okay, try this one on your own. So this is AP question, right? What is the linearization of F? So linearization, tangent line. So automatically, like, I can eliminate A because it has to be some kind of X in it, right? So 1, comma, what's my Y value? E, right? F of 1 is E. What's F prime? E to the X. F prime of 1 is E also. So this is my M, and this is my point. So Y equals E plus E times X minus 1. That's not an option, so let's simplify. EX minus E, the E's cancel out, and we just get EX. The answer is B. All right? So don't get bogged down by the weirdness, right? So just go through that process. Find your point, find your slope, write your tangent line. All right, here's another one. Pause and try on your own. Find the linearization at x equals 0. So again, we are looking at a y equals or an L of x equals. Let's see, we need f prime of 0. That's cosine of 0 is 1. Right? So L of x equals my y value plus 1x. So 1 plus x. So that means to estimate L of 0.1 would be 1.1. So now this is a good one because we don't actually know the antiderivative of cosine. I don't know what L would be. So this is a way of doing this when we don't have any idea what the original function is. We can't integrate or find the antiderivative of cosine of x squared. We don't have that capability. Okay, so now here again is what it looks like on the AP test. This is a pretty common like sub question. It's a part B a lot. Like they'll ask you something and then you'll use it later. So write the equation of the line tangent at x equals 1. Right? So writing our tangent line. So we have 1, comma, what's our y value? -4, right? And then what's our m? Our m is the derivative at 1, so 5. So that's nice and easy, right? So y equals my y value plus 5 times x minus 1. Use the line to approximate the value of f of 1.2. F of 1.2 will be approximately -4 plus 5 times 1.2 minus 1. You can actually leave it like that, or you can actually calculate it. It's up to you. On the actual test, I would say leave it, but I'm going to actually figure out the answer. I got -3. Is this approximation greater than or less than the value of 1.2? Give a reason. All right, so look, if you haven't read the problem, read through the problem. The answer is in there. It says, let f be a function that is differentiable. The table gives values of f and its derivative for selected values. The second derivative has the property that f double prime is always greater than 0. So what is that telling you? That this thing is concave up, which means the tangent line is going to be below the graph. So this is an underestimate, right? So -3 is an underestimate, since f double prime is greater than 0 for all, I can spell, not fall, for all. For all x, f is concave up, thus the tangent line lies below the curve. The y value is an underestimate. Running out of space. Oop. Yeah, I hit a button. underestimate. That's supposed to say underestimate. Underestimate. Sorry, there's a button in the way. I can't type it or write it. All right, last one. Let f be differentiable function such that f of 3 equals 2 and f of prime of 3 is 5. If the tangent line at 3 is used to find an approximation to a 0 of f, then the approximation is. So again, tangent line. So y equals. Now, if you want to do y minus, I do that a lot of the time. So I've got 3, 2, and I've got m is 5. If you prefer to do this, it's the same thing. It doesn't actually matter. It's up to you. I do both. All right, so here is my tangent line. Now it says find an approximation to a 0. What are we going to do there? An approximation to a 0. What's a 0? It's a root. It's where this guy crosses the x-axis. So we're going to set y equal to 0 and solve for x. So 2, 5x minus 15. So 5x minus 13 equals 0. So x is 13 over 5. So that's 2.6. So C. So we can approximate the 0 using the tangent line. That's it. All right, so you have a worksheet. You're not going to be doing all of it, so make sure you pay attention. I'll tell you which problems I want you to do in class or in the classroom. All right, bye.